We are rapidly transitioning from an era of bespoke monumental events to essentially treating orbital logistics like commercial freight.
And that transition is exactly what we are digging into today. The SpaceX Starship program is just moving at this blistering pace, and we've pulled together an incredible stack of sources for this deep dive to understand the reality of where it stands right now.
There is a lot to cover.
There really is. We're drawing from a highly technical breakdown in the new space economy, some great insights on SpaceX's robotics integration, a Space Nexus performance analysis, historical context from Grokipedia.
Dense stack of material for sure. But what stands out to me is that analyzing this properly means we can't just look at the raw specifications of a rocket engine or a fuel tank.
Right. Okay, let's unpack this.
Yeah.
Our mission for this deep dive is to figure out how this specific machine, specifically as it transitions into its massive V3 configuration, is fundamentally rewriting the economics of human history.
It's a big claim, but the data backs it up.
Exactly. But to understand the 2026 reality, we first have to look at how SpaceX engineers actually build things, right? Because it's a completely counterintuitive strategy compared to how traditional aerospace operates.
Oh, counterintuitive is an understatement. I mean, the legacy approach to building a launch vehicle is essentially design it perfectly on paper, freeze that design, build it once, and then just pray it works, because a single test vehicle is way too expensive to lose.
Right, the traditional, artisanal method.
Exactly. But SpaceX employs a hardware-rich philosophy. They treat physical rockets almost the way Silicon Valley treats software.
Move fast and break things.
Yes, literally. You build prototypes rapidly, test them until they fail catastrophically, and then you feed that physical empirical data directly into the next serial number on the assembly line.
Which we saw with the earlier, smaller suborbital prototypes a few years ago. I mean,
Yeah.
they were launching those stainless steel silos, essentially, to just prove the physics of a belly flop maneuver through the atmosphere.
Yeah, the SN8 through SN15 days, it looked crazy, but it worked.
It did, and the iterative process has just moved incredibly fast since then. They ran through Block 1, which, proved the integrated vehicle could reach orbit. And then Block 2 acted as a transitional phase. That's where they added electric thrust vector control instead of the heavy hydraulics and implemented that payload bay they lovingly call the PEZ dispenser to launch Starlink satellites.
And Block 2 served its purpose before being retired after Flight 11, back in October 2025. The data from those transitional flights paved the way for the current generation. Which brings us to Block 3, or V3.
V3.
Yeah, and V3 is not a software patch or a subtle upgrade. It is a fundamental redesign of the vehicle's entire architecture.
Let's talk about the scale of V3, because it is genuinely hard to wrap your head around.
Yeah.
The stack stands 408 feet tall.
That's 124 meters, just towering.
Right. And the goal is to haul over 100 metric tons to low Earth orbit while remaining fully reusable. But the heart of this entire system, the thing making that insane payload capacity possible, is the Raptor 3 engine.
Oh, the Raptor 3 is a beast.
It is. The Super Heavy booster utilizes 33 of these engines, and the ship itself has been upgraded to carry 9. So that's 3 optimized for sea level pressure and 6 optimized for the vacuum of space. The raw power here is just staggering. It's 330 tons force of thrust per engine.
And that thrust metric is a 50% increase over the previous generation. But the real engineering marvel there is the chamber pressure.
Yeah.
The Raptor 3 operates at a mind-bending 350 bar.
Wow.
Yeah, to put 350 bar into perspective, that is roughly equivalent to the crushing pressure you would experience if you were swimming 2 miles beneath the surface of the ocean.
That is terrifying.
It is. The combustion chamber is essentially containing an explosion that violently wants to rip the engine apart millions of times a minute.
Okay, so I'm looking at photos comparing the older engines to the Raptor 3.
Yeah.
And traditional rocket engines, they look like a bowl of spaghetti.
Oh yeah, wires everywhere.
Right. There are external pipes, sensors, wiring harnesses, thermal blankets just all over the place. But the Raptor 3 looks like a smooth, solid block of metal. All the messy exterior plumbing is completely gone.
It's remarkably clean.
But wait, this is where I'm stuck. If they removed 40% of the parts and drastically simplified the exterior, like going from a tangled 1950s telephone switchboard to a sleek modern smartphone.
That's a good analogy, yeah.
Thanks. But how is it successfully handling 50% more thrust? and that crushing 350 bar pressure without literally melting into slag.
Okay, so they achieve this through what's called a full-flow staged combustion system with fully integral cooling channels.
Integral cooling channels.
Right. Essentially, the cooling circuit isn't a series of pipes bolted onto the outside of the engine anymore. The cooling channels are 3D printed directly into the internal metal walls of the engine itself.
So instead of wrapping the engine in heavy, fragile heat shields to protect it from its own exhaust, they are routing ice-cold liquid methane fuel right through the metal veins of the engine wall before burning it.
Exactly. The fuel is the coolant.
It's like running freezing water through the walls of an oven so the oven itself never melts.
That is an excellent way to visualize it. And that internal elegance is the absolute linchpin of high-frequency reusability. I mean, when you eliminate the external plumbing, you eliminate the fragility.
Because there's less to break.
Precisely. You don't have to spend weeks inspecting every single pipe joint and replacing thermal blankets after every single flight.
Okay, but pushing immense power out the back of a rocket is only half the battle, though. If you want a reusable system, you have to survive coming back.
The hard part.
Right. And coming back means slamming into the Earth's atmosphere belly first at Mach 25. That friction generates surface temperatures over 1,400 degrees Celsius.
It's a plasma bath.
Yeah, and in the early flights, we saw the ceramic heat shield tiles literally shattering and shaking off the ship, leaving the bare steel hull exposed to plasma.
Surviving Mach 25 required a radical redesign of their thermal protection system, or TTS for V3. The simple ceramic tiles were just too brittle for the acoustic environment of launch and re-entry.
They were just vibrating off.
Basically, yeah. So they shifted to Gen 3 tiles, combined with metallic TPS elements in the highest stress areas. They also developed advanced gap fillers to prevent that superheated plasma from cutting through the microscopic seams between the tiles.
And they also introduced transpiration cooling, right?
They did.
Which is wild. They are actively pumping liquid methane through microporous surfaces on the hottest parts of the ship, like the forward flaps, to create a protective film of gas. Essentially, they engineered the steel to have microscopic pores, allowing the spaceship to literally sweat methane to create a thermal barrier.
It's an incredible piece of engineering.
I love the visual. I really do. But I have to challenge the logic here. I mean, doesn't intentionally pumping highly flammable methane gas out of the ship's nose during a 1,400-degree re-entry sound like a terrifyingly complex risk for a company trying to simplify things?
I mean, it does sound like adding fuel to a fire, literally, but the physics at that specific altitude tell a different story.
Okay, how so?
In the upper atmosphere during the most intense heating phase of reentry, there simply isn't enough ambient oxygen for the methane to combust outside the ship.
Oh, because it needs oxygen to burn.
Right. So instead of burning, the liquid methane absorbs the immense heat from the hull, turns into a gas, and carries that thermal energy away into the slipstream.
Wow. And this thermal survival mechanism creates a fascinating ripple effect. Because they found a way to survive re-entry without adding thousands of pounds of heavy ablative heat shields, they kept the vehicle light enough to implement the Mechazilla catch.
Ah, yes. What's fascinating here is that the Mechazilla catch is where the rocket equation gets completely turned on its head.
Explain that for us.
Well, in aerospace engineering, every single kilogram of structure you add to a rocket, like heavy metal landing legs, is a kilogram of payload you cannot put into orbit.
It's a zero-sum game.
Exactly.
So rather than putting landing legs on the booster, they built a 146-meter launch tower with massive mechanical arms.
The chopsticks.
Chopsticks, yeah. And the booster just descends, hovers, and the tower simply catches it out of midair. I mean, they first pulled this off on Flight 5 back in October 2024, and then repeated it flawlessly on Flight 7 and 8.
It's still crazy to watch.
It is. And the sources also note a second tower is nearly complete, meaning they could theoretically be catching one booster while fueling another.
Right. And when you remove the landing legs, you drastically reduce the dry mass of the booster. That saved weight directly translates to increased payload capacity. But the catch mechanism introduces an entirely new challenge. If you can catch a booster and have it ready to fly again in a matter of hours, your bottleneck completely changes. The launch pad is no longer the limit. Your limit is the physical number of upper stage ships you have available to put on top of that booster.
Oh, I see. Which means you can't rely on traditional handcrafted aerospace manufacturing anymore. You need rockets built at the speed of the automotive industry. You need a massive factory.
Enter the Star Factory.
Right. The Star Factory in Texas is their answer to that bottleneck. It is a 1 million square foot facility designed with the singular, unprecedented goal: producing one Starship every single week.
A 400-foot spaceship a week. It's almost absurd.
It is. And the sources say they have automated the engine production to churn out over 800 Raptor engines a year, running 247.
That volume is unheard of in this industry.
But here's where the operations start blurring the line with science fiction, okay? The reports outline the integration of Tesla's Optimus V2 humanoid robots into this manufacturing process.
The robots are wild.
Yeah, these robots have 11 degrees of freedom in their hands, they run on AI neural networks, and they are actively handling repetitive and hazardous tasks on the assembly line.
Zooming out for a second, the logic of putting humanoid AI on the factory floor becomes clear when you look at their end goal.
Which is Mars.
Exactly. If your ultimate objective is to establish a permanent human presence on Mars, you cannot rely on a supply chain that ships every replacement bolt and welding torch from Earth.
Right. Amazon Prime doesn't deliver to Mars.
Not yet, anyway. Furthermore, the distance to Mars creates a communications delay of up to 20 minutes each way, making real-time remote control of machines completely impossible.
Hold on, though. Robotic welding in a controlled Texas factory makes total sense to me. But deploying legions of humanoid Optimus robots to build habitats on a hostile planet, isn't this where a brilliant engineering business plan bleeds a bit too far into a Hollywood movie pitch? Like, how close are we actually to autonomous off-world factories?
Well, we are in the foundational proof of concept stages, definitely. But the stepping stones are being laid right now. You need modular automation that can utilize in situ resources.
Using what's already there.
Right. For example, utilizing the Sabatier reaction. This is a chemical process where autonomous machines take carbon dioxide from the Martian atmosphere, mix it with hydrogen, apply heat, and synthesize methane fuel and water.
Wow.
And to do that, you need highly capable robotics. SpaceX's approach is to build the automated infrastructure here on Earth, work out the AI neural pathways in the Star Factory, and then scale it. The sources even highlight a scheduled February 2026 demonstration with Caltech and Momentus, utilizing robotics to autonomously assemble an orbit truss in the vacuum of space.
Okay, so they are actively proving out the orbital construction techniques today.
Yes, right now.
And all of this rapid prototyping, the automated manufacturing, the robotic catches, it is all driving toward a very specific near-term destination. And that's returning humans to the moon with NASA's Artemis program.
The moon is the proving ground.
Right. Artemis the Third and Four are relying heavily on a highly specialized variant of this vehicle, the Starship Human Landing System, or HLS.
And the HLS variant is a fascinating departure from the standard Starship architecture. Because the lunar lander will only operate in the vacuum of space, traveling between lunar orbit and the moon's surface, it doesn't have to deal with Earth's atmosphere.
Right, no air on the moon.
Exactly. Therefore, it completely strips away the heat shield and the aerodynamic control flaps.
It also adds a ring of mid-body landing thrusters, which is super interesting. When it makes its final descent to the lunar surface, it can't use the massive main Raptor engines at the bottom because they would kick up a devastating high-velocity storm of lunar dust that could literally damage the ship or the surrounding equipment.
Lunar regolith is like shattered glass. You don't want that flying around.
Exactly. But getting the HLS fully fueled and ready in orbit presents a monumental logistical hurdle, which is orbital refueling. To get to the moon, SpaceX has to launch a specialized depot variant of Starship and then launch up to 15 tanker variants to fill that depot up with cryogenic methane and oxygen.
That's a lot of flights.
It is. Only then can the HLS dock, fill its tanks, and break Earth orbit.
The orbital refueling architecture is perhaps the most technically daunting phase of the Artemis program. I mean, in the vacuum of space, managing incredibly cold liquids like cryogenic methane is an absolute nightmare.
Because of the temperature swings.
Yes. When sunlight hits one side of the fuel tank, the liquid rapidly heats up, turns into a gas, and boils off into space.
Yeah.
This is where NASA's deep collaboration becomes absolutely critical. NASA isn't just an investor writing a check here. They are actively sharing decades of legacy expertise.
Right, they've been doing this for a long time.
Exactly. NASA's Cryogenic Fluid Management Portfolio Project is helping SpaceX model fluid dynamics in zero gravity and develop advanced low-leakage valves to prevent that boil-off.
And the knowledge transfer goes both ways, too. NASA is gathering unprecedented data to ensure the HLS succeeds. Like, They installed the Scale PSS camera system on the Blue Ghost lunar lander, specifically to study how engine plumes interact with the lunar surface.
Very smart.
Yeah, and they were running massive vacuum chamber tests at the Langley Research Center, firing hybrid motors into simulated lunar regolith. Plus, NASA's Safety and Mission Assurance team even conducted a massive tip-over study.
Oh, the tip-over study is exhaustive.
It is. They analyzed uneven regolith, hidden craters, landing leg compression, and they identified 17 categories and 340 distinct causes for why a lunar lander might tip over.
NASA brings decades of rigorous, exhaustive risk analysis to the table, like mapping out 340 potential tip-over scenarios. And SpaceX brings unprecedented speed, massive payload capability, and hardware-rich testing. It is a really interesting synthesis of two vastly different engineering cultures.
It really is.
And NASA is also planning for the 2030s, looking at large cargo landers capable of delivering 12 to 15 tons of infrastructure to the moon, including a pressurized rover for JAXA, the Japanese space agency.
Wow.
But NASA is also cautious. To ensure they aren't entirely reliant on one massive, complex system, they contracted Blue Origin's Blue Moon Mk2 lander for the Artemis V mission, providing what they call dissimilar redundancy.
Which makes sense, but I have to jump in on the fragility of this HLS refueling plan, though. Because NASA spending years identifying 340 ways the lander can tip over on the moon is incredibly thorough. Sure.
Very thorough.
But before we even get to lunar orbit, SpaceX has to launch a depot and then launch maybe 15 consecutive tanker flights to refuel it. Isn't this an incredibly fragile supply chain? I mean, if one tanker gets grounded by weather in Texas or a single valve sticks, causing the fuel in orbit to boil off faster than it can be replenished, doesn't the entire Artemis timeline just collapse?
It is undeniably a high-wire act of logistics. The dependency on a rapid, flawless launch cadence for those tankers is the single biggest risk factor for the Artemis III timeline.
The single biggest.
Oh, absolutely. If the orbital refueling chain experiences a delay, the mission holds. The cryogenic fuel dictates the schedule. This reality is exactly why SpaceX is pushing so aggressively to finalize that second Mechazilla tower and operationalize the V3 catch system. They absolutely must achieve aircraft-like turnaround times to make that refueling architecture physically and economically viable.
Man. Well, with timelines so tight and the orbital architecture so complex, it is no surprise that the traditional aerospace industry and, SpaceX's competitors are raising alarms. So let's talk about the economics, the skeptics, and the industry shakeup.
The projected cost delta is what is truly fracturing the industry right now. Starship's target marginal cost is under $10 million per launch.
That's absurd.
It is. When you divide that by its 100-ton capacity, it works out to roughly $67 per kilogram to low Earth orbit.
Okay, let's translate those numbers into an impact for you listening. For the cost of producing one average Hollywood movie, SpaceX could literally put a fleet of 15 fully fueled, massive commercial space stations into orbit.
It completely changes the math.
It really does.
Yeah.
I mean, compare that $10 million price tag to NASA's Space Launch System, the SLS, which costs over $2 billion per launch.
Right.
Or United Launch Alliance's Vulcan rocket, which averages around $214 million. If Starship hits its marginal cost targets, it doesn't just undercut the market, it creates an entirely different economic paradigm.
You wouldn't need to spend millions miniaturizing satellite components anymore.
Exactly. You could just launch heavier, cheaper, off-the-shelf electronics, and we're already seeing the market react. Voyager Space signed a $90 million contract to launch their Starlab commercial space station on a single Starship in 2029.
But the path to that $10 million launch is fraught with massive regulatory and technical hurdles. Regulatory delays are a constant friction point. I mean, the Federal Aviation Administration has grounded flights for months at a time to investigate anomalies.
Yeah, which we've seen a lot of.
Yeah, and there are also ongoing NEPA environmental reviews concerning the impact of the Boca Chica launch site operations on local wildlife habitats.
And competitors are definitely feeling the pressure and pushing back. ULA and Blue Origin actively complained to the FAA that SpaceX's massive launch cadence is crowding out shared launch infrastructure and delaying their own schedules.
And the technical skeptics have plenty of ammunition, too.
Oh, for sure. During the Block 2 testing phase, there were some serious explosive anomalies. Ship 33 was lost to harmonic resonance. Basically, the acoustic vibrations from 33 Raptor engines firing simultaneously matched the natural frequency of the steel hull, literally shaking the rocket to death from the inside.
It just rattled itself apart.
Yeah. And Ship 34 suffered an engine rapid unscheduled disassembly. So skeptics point to these events and argue that clustering 33 engines under a massive stainless steel bomb is an inherently flawed architecture.
This raises an important question and highlights a fundamental clash in risk tolerance. As we discussed earlier, traditional aerospace views a rocket shaking itself to death as a catastrophic failure of engineering. SpaceX views it as successfully purchased acoustic data that they can use to reinforce the hull of Ship 35.
Right, just buying data.
Exactly. But a reckoning is coming. When SpaceX transitions from flying empty steel prototypes to flying human beings, the FAA and NASA require a completely different statistical reliability. SpaceX will have to prove that their rapid iteration hardware can eventually hit the rigorous safety margins required for human spaceflight.
Then there's the financial skepticism. Tory Bruno, the CEO of United Launch Alliance, publicly called SpaceX's rapid turnaround model economic nonsense, unless it is heavily subsidized. I mean, SpaceX has spent well over $5 billion developing Starship so far. Aren't they essentially subsidizing this entire experimental program with the massive profits from their Falcon 9 launch monopoly and their Starlink internet revenue? Like, is this promise of cheap access to space actually just an economic illusion funded by a billionaire's deep pockets?
It is a highly valid critique, honestly. SpaceX is absolutely leveraging its market dominance with the Falcon 9 and the massive cash flow from Starlink to fund Starship's research and development burn rate.
It's a huge burn rate.
It is.
Yeah.
But if they successfully operationalize V3, if they can genuinely catch the booster and the ship, inspect them, and relaunch them multiple times with minimal refurbishment, the marginal cost will mathematically plummet.
So the upfront cost is huge, but it pays off.
The upfront capital expenditure is astronomical, yes, but the long-term unit economics of a fully reusable system simply cannot be matched by competitors who are building multi-million-dollar rockets only to throw them into the ocean after a single use. It's an immense financial gamble, but it is deeply grounded in the physics of reusability.
Okay, so what does this all mean for you listening right now? Why should a 408-foot steel cylinder in South Texas matter to your daily life?
It's a fair question.
Right. Well, whether you are a software engineer, a market investor, or just someone who occasionally stares up at the night sky, Starship V3 represents a historical inflection point. We are moving from a bespoke, artisanal era of space exploration into a mass transit industrial era.
Completely.
Your future global internet connectivity via Starlink V3, upcoming off-world scientific discoveries, and potentially the entire orbital economy of the 2030s will ride on the back of this specific vehicle.
By removing the traditional constraints of mass and volume, you really democratize access to orbit. When the cost of getting to space drops by an order of magnitude, humanity doesn't just do the same things cheaper, we gain the ability to do entirely new things that were previously physically impossible.
Exactly. And I want to leave you with a thought to chew on, something that expands beyond the technical sources we covered today.
Oh, lay it on me.
If a single private company successfully achieves a marginal launch cost of $10 million for 100 tons, they won't just control space commerce. They will effectively dictate the geopolitical infrastructure of the inner solar system. I mean, think about it. Who writes the laws when a private corporation possesses a transportation network capable of moving more tonnage into orbit in a single week than every nation on Earth combined has moved in the entire history of spaceflight?
Wow. It shifts the balance of power from nation-states to commercial entities in a way we really haven't seen since the East India Company, but on an interplanetary scale.
It's a massive concept to think about the next time you hear someone casually mentioning a 100-ton orbital payload.